Have you ever wondered why it's harder to breathe at the top of a mountain, but we feel completely fine at sea level? That difference, my friends, is because of atmospheric pressure, the invisible force pressing on us every moment of our lives. So, what exactly is it? The atmosphere is a huge layer of air surrounding our Earth. And because air has mass, it has weight, which means it presses down on everything. This force per unit area is what we call atmospheric pressure. Let's say that again using a formula: pressure equals force divided by area. At sea level, this pressure is approximately 1.013 into 10 to the power 5 pascals, or about 76 centimeters of mercury in a barometer. Even though we don't see it, this pressure is constantly acting on us, and it's quite significant. As shown in, a column of air above a surface pushes down, creating pressure just like a pile of books would do on a table. So why does the air exert pressure at all? Well, air is made up of countless gas molecules. And these molecules have mass, which means they are pulled down by Earth's gravity. This entire column of air above you has weight, and that weight results in pressure. And here's something interesting: this pressure doesn't just act downward. It acts in all directions: upward, downward, sideways. But why don't we feel crushed? That's because the pressure inside our bodies is equal to the pressure outside. They balance each other perfectly. For instance, a newspaper lying on the ground doesn't get flattened. Why? Because air pressure is equal on both the top and the bottom, keeping it in place. Isn't physics wonderfully balanced? Okay, now let's put this invisible force to the test. There are some classic and mind-blowing experiments that prove atmospheric pressure exists. Let's start with the tin can experiment. Heat a little water inside a metal can, seal it, and let it cool. The can collapses. Why? Because the air inside gets removed and the pressure from outside crushes the can. Then there's the inverted glass of water. Fill a glass, cover it with a card, flip it, and the water doesn't fall. Atmospheric pressure is holding it in place from below. Or try a rubber sucker on a wall. Press it, remove the air, and atmospheric pressure pushes it against the wall tightly. These fun visuals show that air isn't just empty space, it's full of force. Now that we know air exerts pressure, how do we measure it? Enter the barometer, a brilliant tool that lets us measure atmospheric pressure accurately. The mercury barometer, invented by Torricelli, is a simple yet genius device. A glass tube filled with mercury is inverted into a basin. The mercury level balances at a point where the atmospheric pressure equals the weight of the mercury column. At sea level, this column stands at 76 centimeters. There's also the aneroid barometer, a modern version with no liquid. It has a metallic chamber that compresses or expands with pressure changes, giving us accurate readings. In the diagram, you see both instruments, the mercury barometer with its liquid column and the aneroid with its pressure-sensitive chamber. Atmospheric pressure isn't constant everywhere. It changes with height and weather conditions. As we go higher up, say up a mountain, there's less air above us. So, the pressure decreases. That's why climbers carry oxygen and boiling water bubbles at lower temperatures in high altitudes. Also, weather systems affect pressure. A low-pressure area usually means storms and rain. A high-pressure area brings calm and clear skies. Though there's no single formula, a good approximation is pressure drops by 1 centimeter of mercury for every 120 meters of ascent. In the graph shown, you'll notice how pressure drops steadily with increasing altitude. Time to test our understanding with a real-world calculation. Let's say we have a table of area 2 square meters and the atmospheric pressure is 1.013 into 10 to the power 5 pascals. How much force is exerted by the air on it? We'll use the formula force equals pressure multiplied by area. That's F equals 1.013 into 10 to the power 5 pascals multiplied by 2 square meters. That gives F equals 2.026 into 10 to the power 5 newtons. That's over 2 lakh newtons, equivalent to about 20 tons. Imagine that, all that weight just from the air above. And yet, the table doesn't collapse because the internal pressure balances it. So, what have we learned? Atmospheric pressure is the force exerted by the weight of air, and it's constantly acting on every surface around us. It affects everything, from weather and climate to flight and respiration. Barometers and altimeters depend on it. Even your boiling pot of water reacts differently at higher altitudes, all thanks to pressure changes. And let's not forget, our very survival depends on this balanced force. Without it, life as we know it wouldn't exist. So next time you look up at the sky, remember, the air above you may be invisible, but it's never insignificant. I hope you now have a clearer picture of this fascinating, invisible force we live within. See you in the next session for another journey through the amazing world of physics.